Wil je het niet als
Ja, dat is het met.
I can hear you, just so you know.
Yeah, maybe they are not active. But look, you can. Okay, so we are already. So hello. So thanks the organizers for inviting me to the workshop on tracking. I will give a talk on the VOT tracking challenge, which has been running 10 years. And I will not use it as like tell you how we do it and just like this is the right way to do it. I actually will say something about mistakes. And it's more like what makes a good tracker and what makes a good evaluator. It's not so easy to sometimes spot good one and bad one. And that was one of the reasons why in 2013 we started this initiative, because hundreds of trackers were published annually, and we were not sure what works or what doesn't work and how to evaluate that. And at the time, there was no standard evaluation, perhaps OTB. And at the time, this source code sharing was so common as now. So there are 4 things that I will talk about: the data set on which we will how to evaluate and how to organize the challenge, because we don't do the challenge only to give someone the gold medal, the plaque, but we want to hear feedback, and we want to give some background and understanding what really is a technical improvement and what enhances performance, and we discuss with the community. So part of my talk is also directed to this. So if you don't like something in the challenge or the way in general tracking algorithms are evaluated, I would like to hear feedback either after the talk in let's say in the broad forum or even privately. It will be very interesting to me. Yeah, so let me try to move the Zoom. I don't see the title of the slide because the Zoom controls are sitting there, and I'm not. I try to maybe okay, and I move them. Okay, so this how we construct the data set. So we believe training does not require. So unless you have 95% plus performance, 100 videos are sort of enough. If it doesn't work on 3, you know, or 15 or 25, you know roughly what the performance is. So, and actually, if you have a lot of data set, it slows down everyone. It costs a lot of cycles. So our philosophy is make it diverse and make it efficient. So keep the data set acceptably small, diverse, challenging, and well annotated. So we spend a lot of time on annotation. So how we proceed, and that's how we started, but we are doing this every year again and again. We scan all the available data. Today, in the talks, there was some idea to follow. We check, we make some first draft. Then we check whether they have certain attributes. We cluster them by attributes. Then we run some standard tracker. Usually, if you want to be declared a winner, you have to provide the code so that we can independently assess. Then we do some sampling to control the difficulty, because we try to make the problem difficult to a level that makes it so that people don't come back with 1% performance. But then we want not to have a tracker which has 95% performance. So we select the difficulty according to the state of the art. And that's how the data set ends up. It used to be 60 sequences. It's interesting, like on my Zoom, this thing disappears after a while, normally, if I don't touch anything to control. So there might be some interesting information lost because of the zoom controls, but that's not important. There will not be anything critical. Okay, so we started early on with bounding boxes, but very soon we realized that segmentations are much more interesting. And we decided to, that's interesting, to go for all-out segmentation tracking. So currently, VOT is a tracking by segmentation. We try to then fit sometimes bounding boxes automatically, but either axis aligned or some optimized fit. But I think this is just introducing issues. From 2020, we introduced also, and this was a request from the community to introduce sequester data set. So something where you couldn't really cook the results. And on the public data set, people self-assess themselves, and they then run maybe for the top 15 trackers. We assess their performance on sequester data, which, by the way, could be quite computationally demanding. So, and we do check everything manually. So although we, of course, use some automatic tools in the process, we do check manually. Okay, so just to give you an idea what happened this year, and although the formal part of the challenge, which will have a winner announced at ICCV, has finished, we have now decided to have a leaderboard and a continuous submissions. So we went from a single object in the image to multiple objects, and we think that good trackers these days include methods to check for distractors, and that actually solves the multi-object tracking. So to me, the multi-object tracking and single object tracking, the single object tracker keeps awareness of possible dangerous distractors. You actually have the multi-tracking problem. So we see that multiple objects, even some including another, like the rider on the bike, unlike what people talked about in the morning, so know that we need to sometimes track parts of objects. So like the hands, maybe you want to do some editing there. So not everything has a semantic name. So for instance, here, where the hand touches the palm, say this is sort of arbitrary, and people might like to track any part of an object. And for that, this type of initialization with a detector might not be possible. There was a recent released data set from underwater videos. So you see that as soon as, so we took it because these underwater videos, schools of fish, have a huge number of densely packed distractors, and also sometimes the fish movement. So we think about it's interesting from the point of view of motion, density, and so on. So we immediately incorporated data. We looked into tracking of transparent objects. That's a challenge. I'll talk about a little bit more later. We looked at articulated objects, things which significantly change their shape. So for this one, I have a video if we want to look at it, but the juggler is spinning the bottle, so there's a blur. I think that I'll talk about this a little bit later on, but I think there's still not yet enough blur in the data set, and blur is somehow connected with motion intimately, but still most of the videos that you see processed are pretty sharp. So that, of course, you can make the exposure time short so that fast motion doesn't create a massive blur, but that means the lighting conditions are good and conditions are good in general. So in difficult conditions, blur will affect tracking. So we also usually remove the easy sequences and replace with the more difficult ones as the field progresses. Maybe it's even difficult for you to see that there is a rabbit running through the avalanche. The butterfly is probably challenging because it changes so much. And maybe it also shows that on the right, the easy ones, it's not so easy for a person to predict which sequences will be challenging for the trackers. And the plot in the middle says that we've actually we've been making the data set more challenging faster than the trackers improved, although they improved enormously. So now this is the data. The data part, if you know about the sequence, set of data, especially annotated, but usually we'll have to re-annotate anyway because we need this precise segmentation. Let us know, especially if it differs from what we've had. So there was a data set, I didn't show it here, from drones, which often they have fast camera motions and so on. So if you see something very different, then we would be glad to introduce that. So for evaluation, so the classical evaluation introduced by OTB is the success plot. It means like what is the percentage of frames where your tracker has an overlap of at least something like 0.5, 0.6. You see that overlap of 1 is almost never achieved. Immediately you go to something like 0.9 and then it goes down. Now, we thought that this is sensitive to the length of sequences, and we thought it was not very informative. And at VOT, we tried to do something which we thought was better. So we introduced this anchor-based protocol. So the tracker would be reset at every anchor. So more or less you knew what the performance was for all sorts of sequence lengths. So we thought, okay, let's remove the dependence on the results on the sequence length, which means on the data set as well. But actually the data set is very important in any case. And our lesson was probably over complex. If you take a random paper on tracking, it's very likely this type of curve will be there because they also probably look good. It's some sort of visually satisfying. Whereas if you have some average overlap number for different lengths, people wouldn't, it's more complicated. So we more or less dropped it. Also, we try to do some tricks, again, making it complicated. So for instance, if a tracker's overlap went to 0 for a short period of time, that would be for us tracking failure. And we didn't want to add noise to the evaluation by saying, okay, if you randomly fail early, you will be punished for until the end of the sequence. So we had some rules, like if there's a few frames when you drop to 0, we'll ignore that. We have somehow moved to some simpler measures now. Also, we realized that the interest of the community, and I think the possibilities of the trackers have improved to a level that we can do long-term tracking, which means we can have total occlusions, we can have situations where the object goes out of the frame and comes back. And we collected the long-term tracking data set, which has this phenomena. Usually these sequences are longer. There we were happy to do axis and line bounding boxes. So this is more or less was evaluated as detectors. Again, a little bit unsatisfactory, because when does a short-term problem becomes a long-term? Okay, occlusion, but if that occlusion is 1 frame, or if something is occluded up to 1% of the area, it's the same thing, and we have to make a hard decision. We also introduced, and you see that we had a broad range of challenges. We introduced the real-time, because the winners around 2019 were methods which took like 5 minutes to process a frame. So there was nothing that would push you towards reasonably efficient solutions. If you want to do that, you had all the time in the world. So we said, okay, if you are not on a certain machine running fast enough that you give me a result at a given frame, you will be given another frame and your performance drops. As of 2022, with this transformer-based approaches, if you look at it here, the top RT trackers were in the top 10 of the short-term tracking challenge, so no need to distinguish that. These days, the problem of my tracker, which can't be called a tracker because it takes 5 minutes per frame, is gone, and most of the best performing trackers are also fast. You see that only one of the well-performing one dropped. It means usually that it was not fast enough to operate at real time. So if we look at the history of VOT, in 2013, we got many diverse trackers, and their story will be that usually whoever gets best in the challenge dominates the submissions in the next year. So around 2014, these discriminative correlation trackers were doing well. Then 2015, reasonably well. There was 2017, some good performance, maybe CNN, Siamese trackers. That lasted for some time. In 2020, that was the last transformer period. In 2021, 17% of the submissions were transformers. They were the best performing, and now last year 45% of the submissions were transformers. So also we see that how the field is changing. Fine. So now after 10 years of VOT, we decided to do sort of a major overhaul, and of course it's important to have stability, but we wanted to simplify things. So we renamed VOTs to VOTS because these days actually we are measuring tracking by overlaps of masks. We are not, and I will be talking about that, doing point tracking. We don't do correspondences. We only say, okay, is the set of pixels belonging to the object correct? And we decided to have a single challenge which unifies single and multi-target and long-term and short-term segmentation tasks. So we have a multi-target segmentation tracking data set, which just means we have multiple objects annotated. The trackers will now be evaluated on sequestered ground truth. So we gave up at the moment on sequestered data because that's sort of doubles the annotation effort, and with the longer term trackers, it's becoming substantial. So we at the moment believe that sequestered ground truth is good enough. So if someone went mad and re-annotated himself, he could do that, but we still can keep, and we did keep some sequences for our purpose. And if the performance on these sequestered sequences was very different, that would raise an alarm. We think that, as I said before, single and multiple target tracking is almost the same thing, because for many applications, if you do an identity switch, this is the same thing as losing a track on one and losing a track on the other. And being aware of the other objects of the same category, it's like a disaster-aware tracker. And we decided that the leaderboard will run continuously. So for instance, for CVPR submission, you can get state of the art, and you will submit the state of the art on the 1st of October or 1st of November, and it will be useful, not like before where perhaps when you miss the deadline for the challenge, bad luck. Now, when I hear all these MOTAs and other characteristics, we have gone for super simplicity. Everybody understands intersection over union, and this thing on the left is for what it was classical in short-term tracking, because the target is present. So, okay, let's your guess. I'm then not sure what is. Okay, let me have a look. Target absent. So the target is the gray thing, and your guess is the red thing. So because in short-term tracking the target was always present, you didn't have these two cases on the right, and actually in the middle one either. So if your prediction is on top of the target, you will have a very high score. The second thing, your prediction is not intersecting with the target, 0. This one didn't happen for short-term tracking. You think that the object is not in the field of view, but it is. You get 0. And now we have the two cases where the target is absent. So if it's absent and you say it's absent, you get 100% overlap. And if it's absent and you don't think it's absent, you get 0% overlap. For this right part, you have either 0 or 1 as overlap. So it's sort of like almost correct answer. Is it visible or is it in the frame or not? But everything then works together. We have everything is between 0, 1, and all these cases work as one. And you can use it. The intersection over union now works as a sort of detection and precision as well. So super simple, interpretable as well. Okay, so now I will talk about some open problems that we don't yet cover in VOT, and maybe the community can direct me that way. So I might go through this fast because this is a result of a paper that I'm working on with my students, and it shows, I'm not sure why, it shows this, what you can do if you have dense correspondences. We saw Adam talking about this in the morning. So you can do nice augmented reality. This is in the case of long-term tracking, so we don't care about these things, that there is occlusion. So as I said, augmented reality, it supports some other interesting applications. So this is style transfer. So the top thing is links, moving a video, and then an artist in the first frame draws his stylization of that links, and you have to, you want to save the artist all the work to do this for every other frame. Same thing here, the actor is doing something, one frame is stylized, and if you have this dense flow, you get sort of animation. The people who are interested in this say this is the state of the art. So coming back to open problems, this video is from 2006, transparent objects. So I saw this miracle thing in 2006. How come he can track the glass? And of course, the method, which was based on some boosted detector, was actually tracking the hand. So this led to a paper where you could track objects which were invisible. So that would be the sequence. If you look at this, this would be a classical shortened tracker. Okay, if it doesn't see, it cannot say anything. This was what people would say. They know that if your hand is in contact, where they assume, like the magicians will play with this, but they assume that your hand is still in contact and they can track the invisible. And this can do it. We had a paper about this, that you get the correlations and then you track very precisely invisible things unless unpleasant things happen. As I said, magicians can play with this. We don't have any data set where, for instance, through two cameras, we could say track the things which are not visible, because it's not ridiculous to ask, where is this object when it's not visible? You still have a pretty good guess. Coming back to now, that was about trying to, let's say, avoid the problem of tracking, let's say, light objects. So you see that if you have a bubble, it can change its shape and changes. It's actually interesting. People think, okay, I see somehow the deformation of the field. In our experience, it turns out that the specularities on these transparent objects help a lot. So you see here that appearance would be very tricky to deal with. So we wrote a paper about this, and it turns out that besides training on specific data, which helped, if you deal, you have to deal with these distractors. So and standard trackers don't do too well because they are not trained on transparent objects. Our stuff is this red one, and we choose Stark and other trackers which performed reasonably well on VOT, and they did. This is another example. You see the specularity. Maybe it looks like for normal objects, it's usually making tracking more difficult, but here it's easier. So you see that we are tracking even this small part there, and then the standard trackers are lost. So maybe this is one domain where data sets are now available, and if it's inserted in the benchmarks, people will take care and it will work well. Okay, one other problem which we don't have in VOT much is fast-moving objects. So if you have an object like a tennis ball which was just hit during a serve, a circle becomes this long line which is sort of transparent because the ball is at different positions during exposure time and you see through it because it's not covering the background all the time. So you see all sorts of effects like arrows, various fast-flying animals, and spike in volleyball makes the ball look like a long extended object. So the fact that this is useful is seen here in this video. So there is an object probably from a camera with very small frame rate flying over, and on YouTube there was a huge discussion that this is a UFO. And messages like this is incredible, blah, blah. And some guy took a demo. We worked on this, the blurring of objects, and he discovered that this was actually some bird of prey. I forgot which one. So this deblurring might be interesting in its own right, but also we have not yet in tracking exploited the connection between blur and motion. So blur is actually an indicator of motion. So it should be taken into account, and I haven't seen a real, let's say, a paper that would be on, let's say, top performing and it would take this into account. This is what you can do if you can solve this equation. So you understand the motion, understand the blur, you can create a super resolution of arbitrary speed, because you understand that the shape that you see at the top, which is interpolated, is an extended thing. Okay, so I will skip this part. Maybe I will just say something about this. Micro expressions are minute, very fast motions, which you can't control. And they show, for instance, this guy here shows that his cards are bad. Yeah? This one here, at this part, there's a small movement. So we have not really tracked this type of movements for detection. Yes, I'll go fast here. This was this is a video that we took in 2011, and it's related to a question which appeared in the morning, that you would like to create some 3D model of the thing that you are working, because if you start rotate, this is fine, this is nothing, shifting in 2D, but when you start rotating, unless you have some 3D model, maybe even or a nerve or something like this, you cannot really understand what is happening, because from segmentations, well, there's not much doing, but you don't understand that you see different parts of the object, and then that you are coming back to the original one after one turn. So I worked with this with a few people with ETH, and what we are trying to do here is actually simultaneous modeling and tracking. And for certain things it works, but so we have some results where we do understand when things turn 360. Maybe the best way to visualize it is this video that Dennis prepared. So you are tracking an object, but in the meantime, you are also creating some sort of very coarse 3D reconstruction. It's not about precise reconstruction. It's about what part of the object you are looking at. And maybe instead of having this type of keyframes and reference, it's about having some simple structure. You see the shape is not very precise. That would allow you perhaps to have some deep representation attached to it. Okay, so fine. Okay, nobody has dared to put something like this into a tracking challenge. This is a split and merge. So it's tracking cells, and we don't even have I would say, I think there's no data set for this, I'm aware of it. And you can have also the other way around, like you have objects which are turned into stuff in a blender. So this is also a problem in tracking. So the conclusion of this talk could be that we have moved a lot there, and there's still plenty of work to do despite the large language models segment almost anything and so on. And thank you. And I'm ready to take the questions. Let's have a look in the chat. No? Okay. Okay, thank you. Okay, thank you. At half an hour, no.
Okay.
Can you ask the Zoom participant?
Yeah, let me ask. Hello. Okay, great.
If they can hear.
Awesome. Okay. Sorry for the interruption. Let's get back to the observation. So what we see is that video understanding model can perform well on very short clip of video, let's say 10 seconds to a couple minutes. So what is about long video? We don't have that. And then on the task side, what we know is that it performs well on very simple tasks. For example, classification, detection, and localization. But let me make another contrast. So, oops, too bad. When you look at a kid, let's say 10 years old kid, you can give him 1 or 2 hour movie, watch that. After that, you can ask him many different questions at different level of difficulty, from a minor detail to high level abstraction, or even like what is the moral lesson of the movie, right? It's interesting. So that it keep bothering my mind. So what are we looking at that, and how big the gap between human perception and machine? So by that, we have a couple of questions we need to understand to move forward. First, what are we missing in our current model? And second, are we currently blocked by lacking up the data set that can deal with long video understanding or tasks to deal with long video understanding, or actually even with block by modeling, let's say our current AI model cannot handle that complicated task, right? But if the belief is the early part, then the next question is, what are the right tasks for long-form video understanding to move forward? So with that observation, today I'm share a couple work to tackle along this line. Hopefully by the end of the talk, we get a little bit better picture about that. I'm not promised that we can solve all of this, but hopefully we can kind of shed some light along this one. Without further ado, let's jump into the first work. So our first work is collaborate with lovely college here. So the paper called Relational Space-Time Query in Long-Form Video. Actually, we have a poster on Tuesday afternoon. Feel free to come for interaction. Let's jump into this one. So the objective for this project is very simple. We want to identify a set of practical tasks for long-form egocentric video understanding. Very long, let's say half hour to 1 hour long. But at that level long, what understanding means? And also, the task necessary to be completely vision focused with well-defined human interpretable metric. Because when we look at some other tasks, let's say if you look at vision and language tasks, it also have long video sometimes. But the thing is, they have some metric. Either they have the language part of it, either in terms of the prediction, let's say for captioning, the prediction have language English, or Q&A, you have the both input query and answer in language. I think there's nothing wrong with that. It's just like it's very difficult for us to do some analysis, like component analysis. We want to know where the model is behind or where the model is advanced. And then it's just confused because we want to know all of the perception visual model, which part is doing well, where the opportunity for improvement. So we just want to kind of try to deploy the task that completely vision focused. So if the first two tasks can be done, then we would like to do like construct benchmark and establish baseline for the task. So objective is clear, but then when we make observation, when we look at long-form video, most of the egocentric video need the machine model to understanding the relational between human activity and object and their interaction. Most of the time you see the cameraman, which is the first person, hand doing some activity with their hand, interact with different objects from time to time. Let's say watching this, watching TV, doing computer, all kind of thing, right? But the current, they are the related tasks, but somehow the current benchmark is study them in isolation. Let's say kinetic, they focus only on the activity recognition. On the other hand, like some hand object detection, like 100 day of hand, just completely study another object, another task in isolation. And when we also look at the Q&A based data set, it's more like focus on short video, or they have a language part in the output or input of the model. So that is hard for us to kind of dive deeper into the model analysis. So with that in mind, we propose the task, the set of tasks from relational space-time query tasks. So the task based on a very simple observation. Every event in the egocentric video, we have like the cameraman engage or perform an activity while interact with a couple of objects or set of objects during some time. Okay, so there are three main parts: activity and object and time. The observation is that by masking either one of them, we can form a query, and then the masking part becomes the answer. Very simple, but we can completely make it templated. So that means we don't have language on it. We just have completely vision part. Let's take a look at the first one. Let's say this is a video from ADL, 30-minute video. So first, if we mask out the activity, so we have activity query templates. So the input is just a graph of instant, like an object, and then a time window between begin and end. And the output prediction is supposed to be a set of activity. Here is a set that means can be empty as well. For example, we can look at that. The first question is, what activity did I do with this object? Like, is it a mark? And then the answer can be making tea. But on the other hand, if I'm asking a different time, let's say not instead of 0 minutes to 15 minutes, I add another time window, it can be none. And because that is during that time, camera will doing nothing with that mark, right? It's very basic. So you bundle together to make the task more complicated. Let's look at the next thing. So the next is that now, what if we mask out the time? So basically the input is activity and object instant. So basically you ask for particular what time I do this activity with this object. It's like a little bit more difficult than activity net, basically more instant based. So you can see when do I take pill with this object, and you can answer sometime or similar like that. Next, you can also mask out the object query. You provide activity label A and then the time window. So you can see what did I interact with, what object I did interact with when I do washing dishes during this time. So basically you can watch multiple dishes or some other object as well. Or it can be none as well. So here you see that the task here is completely vision-based because there's no language part. You just give, for this one, you just give like activity label and then time window. And also sometimes you have a graph of an object instant and you do matching. Okay? So now this one requires a little bit different way of annotation. So we start to do bottom up, then densely collect the low level annotation from the activity timestamp, object annotation in bottom box, and also the interaction. Let's say when the object been active by the camera wearer or not. So when you interact with that object, and then we can write an engine to automatically generate the query. So you can mask out and you generate a query, but it can be done very carefully because you want to balance the answer. That means there's no skew distribution, be biased in the answer, so that the model can pick up that quickly. And then here the result data set. So basically the main here that we adopt ADL and Ego 40. And normally it's around 15 to 20 minutes long and with like a couple 100,000 of query. This is simple compared with the other QA page. It's much longer in terms of the length of the video. So now take a look at the baseline. So in order to approach this problem, we can first think about a modularized baseline. Because if you think about it, problem seems to be complicated, but each component can be known, right? Let's say we can start with an object detector, can be stay up the object detector like Massacinen or deter, or even open work object detector like OLN or GNN. So just like given a video, you generate a bunch of proposals across the video. Or you can slide a window of 2 seconds to do classification of the action to all of stay up there. And XOI detector is provide a box like bounding box of the objects. We just tell whether it's been active by interact by the camera wearer or not. Or the object matching, like given 2 box of instant, like 2 crop of images. We want to know whether 2 box, like 2 embedding of that, it come from the same object. More like you want to do instant matching between the query crop part with the thing that you detect in the video. So all of them, you can plug them together, just component based. Basically, it's just bottom up and more like at least it, right? You do everything, it just stay up there. You want to know what if I put a bundle stay up there model for every individual problem, how far I can solve this problem. It's just simple. We want to understand that to see the limit. On the other hand, people say, hey, I can do end-to-end top-down. Let's say both implicit approach, like transformer by attention by. In that sense, we can adopt tip deter or object transformer to end-to-end from the query and answer to the end. So see how fast it can go. So now, interesting, let's take a look at the modular baseline. First, the metric here is just because there's none as well. So we have like recall at 1, recall at 3 for activity query, object query, and time query. So we can say ADL is a little bit easier because the pixel is not that complicated as Ego 40. So you see, Ego 40 is very challenging for this task. And even for ADL, the number also low in the sense of recall at 3. But let's compare with the top-down and the bottom-up approach. So you see, even in this case, the top-down is a little bit lower than the explicit, the bottom-up approach. But it's still early to say because it's still more, and then we haven't do anything optimize the top-down attention-based model. It just gives some sense how challenging it is. You see, random change is very low here as well. So then we can go ahead and do some kind of oracle analyze. We take the modularized model, we replace it of the detector by route truth. So the first thing you can see is that here Even on of the other two is route truth and only the object matching a prediction. It's pretty much easy for it just indicate the object matching, like instant matching using features seem to be easy. For object query, it can be 100%. And the other one is doing okay. But then if you look at the first row and the last row, it's just like about you switch the prediction of action recognition with the route truth. So you see, if you switch it by the route truth, even the other with prediction, you see 10% or 20% improvement. So here the opportunity for improvement is on improve your activity recognition module. Okay. So now we even go ahead and say want to do like label analysis, where we want to understand the correlation between the subtask with the whole query task. So you see this plot is more like on the activity query class. This is object query and this is time query. And its curve is that when you take one of the label space, you just try to corrupt it. You assume that at the beginning, all of the component is perfect, but you corrupt it to make it like less imperfect, right? And then if you see the blue curve is more like you inject noise into activity recognition, it affects all of the three tasks. So that makes sense. But you see the rest and the green one is just interaction detection or the object detection. It just only affect the object query. So that somehow we can get some correlation between the tasks, right? Yeah, the observation I just mentioned. And in conclusion, what we found is that long-form video understanding require modeling various related subproblems in the same framework. Even though the subtask like well-known and seem not very challenging, but when you bundle them together, it becomes extremely challenging, but yet interesting. And then we provide REST is a good framework for studying long-form video understanding. So I think for the sake of time, I move to the second one, and at the end, I will take all the questions. Okay, now let's move to the second part. The first part, I already mentioned about how to handle long video. This one, I focus on how to handle complex tasks. So in this one, we introduce a new task called space-time semantic correspondence. This is John work with Guises. So before that, let's first look at semantic correspondence problem in literature. So it's a very fundamental problem in literature. In the image, even it can date back to 2008 or even earlier than that. Basically, very simple. Even pair of image, sort and target, and a set of key point and sort, and you want to predict the correct semantic correspondence on the target using zip flow or even before deep learning, right? And then recently, the problem also been studied in the video domain, where they try to do dense correspondence matching, which in given a two video, they do alignment. So every frame, they find alignment on the other video. So they call temporal dense alignment. So we look at that problem. What we want to do actually a little bit more complicated than that. We want to do is not just space, but also in time. The problem formally defined is given a pair of video, one short and one target video, and a set of space-time key point from the short video. We want to find the semantic correspondence on the target video. So, and then in time alignment, we need to align by key moment. What do we mean by key moment? If you look at the polling, the key moment was something like the first one when the bowler fully swing back the hand, that's the key moment. And the other key moment is that when the ball released by the hand. You see, that's one is the second key moment. And then this is actually prediction from the model. On the right example, you can see the key moment can be the liquid start pouring, and then other liquid stop pouring, right? So spatial, but in this case, we want to have like space-time alignment at the spark key point, but in space and time. So the next question is, why do we care about this problem? So why it matter at all, right? The reason why we are excited about this problem is that they have many practical applications. Let me list a couple, hopefully can excite you. For spark analysis, you want to compare different layers. So which one play and what are they different? You want to compare Messi and Ronaldo or something for offshoot, right? Or you want, in activity coaching, you want to compare a professional golf player with the novice to see how they're different. Or even like you compare with yourself a month ago, a years ago, how you do bowling or golf. Do you do any improvement? In robot imitation learning, where the robot want to see the teacher doing some tasks on the Excel view, and then they see themselves doing that in the ego view and then try to imitate that. So there's many correspondence, but this is necessarily happen in space and time. And secondly, we think that it's a fundamental task for video model. It's actually very challenging because it requires model to understand the key moment, the object involved in the interaction and their interaction to complete the task well. So let's zoom into this one. So how to annotate that? We adopt the current available pen action data set. So the key moment, you can see it defined here for different kind of action. Let's say if you see golf win, the key moment is that's when the stick fully back. The other moment the stick hit the ball. And similar, you can see like tennis forehand, where the racket is fully back, a racket touches the ball. Similar like that, there's plenty. But we're not just interested in the key moment. At the key moment, we interested in the key point, which is on the human key point, as well as the object involved in this one. The object part is more difficult because most of the time the object is small and very fast moving. So you see like in baseball, it can be the ball on the bat, or golf stick and ball, or racket and ball, and so on. Okay, so with that, we annotate them and we have the data set with about 40,000 training pair and 20,000 validation pair. And here we have to set up because pen action, you have totally 13 key points on the human, but we have only up to 3 key points on the object. It's not like balance. So we can create another subset setup where we just have 3 key points on the human and another 3 key points, up to 3 key points in the object for more like balancing. And for the 3 we choose more like left wrist, right wrist, and the head. And then the other key point on the object. So make it more balancing. And similarly, we also annotate a pouring data set where you have the liquid start pouring or liquid end pouring. And you see the key point here across the corner of the cup, the fingertip, or the hand, or so on like that. Let's look at some of the video. So in this case, it may be a little bit small, but you see at the key moment, there's a button box, and then you see some key point. And then this one is based on swing. That's fine. Let's play it. So it's not play. Yeah. So when the ball release, you can see, let's see the drop wins. So when
Okay, I found this on the web for drop wins. Check it out.
okay, when it hit, you see the key point. But the more challenging are the swat. The reason why it's challenging because at the key moment, it's very similar both. It's only different in the motion when you see it go down, right? On the way down. And when you go up, the ball and the location of the key point is exactly the same, only direction of the motion different. This is the more challenging one. Okay. We'll come to that later. Okay. And then similar like tennis backhand. Actually tennis forehand. And tennis serve, like when the ball released from the hand, the ball on the way up to the sky, and then the racket hit the ball. At that moment, we want to align key point on the object and on the human joint. So that is challenging, and a lot of fast motion. We see something challenging. We will talk. And then now let's take into the baseline, because this has setting some similar with the reverse problem where we have only time alignment or space alignment. One question people can ask, why don't we just decompose this problem into time alignment and space alignment? Let's say first do time alignment. After that, we can do space alignment. Simple, right? Why just make the problem complicated? Just do that. And we have that baseline as well. So, but for the time alignment, basically you can extract internet features or some sort of feature like Moco, and then you can do nearest neighbor search, very naive. Or you can do dynamic time warping on the features. Or you can do time cycle consistency, which actually stay up there time alignment method. On the space option, we can use CAT, which is stay up there visual semantic correspondence using transformer. But one people say there's a many human key point. Why model cannot check by using bow matching, right? You can do bow estimation and match across the bow. We can do that for sanity check, whether model can check by do bow estimation. Let's look, and then on the other hand, we say, can we approach this problem directly in space and time rather than decompose them? So yes, and in that sense, we follow the same traditional approach in correspondence problem. Basically, instead, they start with the deep backbone CNN, in image, but now we brought in video, we just use 3D CNN and feature extract at different layer, and it can be upsampling and downsampling to get into the same side of the feature map. After that, you can concatenate the feature map and you can compute a correlation metric. That is just like feature backbone extraction, nothing more, less. This one have option that you can keep it erosion or you can backbone full fine tuning end to end. Now, the other component is you can have the aggregation network. Basically, we can adopt the CAD model. CAD is the state-of-the-art image. We just extend it to 3D. So if instead of 2D, we extend it to 3D. And then just a bunch of projection, transformer, and transpose and transformer, and predict it in the correlation in the feature map. And then we can do upsampling to the flow, like the spark displacement flow of the correspondent. That's simple, and L2 loss. But we said that maybe that's a problem, it's just simple. Why don't we just use 3D CNN? Actually, we have another model called Symbol Aggregation Network, or ANN. So basically take this and we just do reshape the correlation to make the same shape, concatenate, do a few 2D convolution layer, and then reshape back to prediction and upsampling. It's the same way. Beside that one, we also have symbol matching, where we take this one and do pooling on this one. It's just called no learning at all. Just take the feature correlation. That's it. Let's take a look at the result. It's so interesting. So now first, if you see here, the problem first, both way perform very poor. I forgot to tell the metric. Okay. So in keyboard estimation, in space, BCK 0.1 in the bounding box is very standard when you compute the distance of the predicted key point with the route truth. And that if that distance is smaller than 10% of the longer side of the bounding box, you say it correct, right? But that is just in space. Now we have space and time. So we have like, we only allow the model misalign in time 1 frame, 3 frame, or 5 frame. And we have like 2 settings, 3 plus 3 is just like only 3 key points and the object, or 13 on of the key point plus object. So in our case, sentinel check both way doesn't work. Even you do like stay up the act bow estimator, it doesn't work regardless how you do time alignment. Now for stay up the arc here, it's no surprise that TCC work the best, but still low. And here we also provide the oracle where we have the route truth of time alignment using stay up the arc space. Then it's still like this. Surprisingly that if you use SD card or ANN, you perform better. Even like symbol feature matching also do reasonably well. So why surprise when we think at the first, but actually it makes sense, because if you decompose the problem becomes harder, not easier, because you don't have to contact up the motion for thing. And then when you do temporal alignment, you lose all of the spatial, which just reduce to the embedding. You don't have spatial. And now you have spatial, and then you have, yeah, but this is just spark problem. So the model can select whatever feature makes sense for them to do space-time together. So that totally makes sense. We go ahead and do a little bit more model analysis. Now, reverse I mentioned why is the most difficult thing. You can see it difficult across even human keyboard or object keyboard or all of them, because of the both and the motion direction is confused. But on the other hand, if you look at the other challenging case here, baseball speech and tennis forehand, the object is very small and very fast motion. When you roll this one, it's just very fast, and a lot of time we see blurry exactly the observation in tracking you see. So it's challenging, but they still do reasonable well. And when we look at the rod key point generalization, model can be trained on 3 plus 3 and test on the other 10, which is completely different set of key point. Performance drop for sure, but it's still a decent number. And then we can test everything. It's just doing okay. And further, finally, we take the model pre-trained on band action, fine-tune it on pooling dataset. Okay, one observation is that when you pre-play this pre-trained model by kinetic pre-train, performance dropped from 12 to 20%. That's surprisingly that initialization of band action for this task is very usual. But remember that the action and the key point in band action is completely different from the action and key point in pooling. So that means there's some sort of generalization for matching in here. And then also it open up the opportunity for, because this data set is quite small, let's say just like 10 or 20 video. So that means it open up opportunity for few short training for kind of key point space and time matching. Finally, there's some qualitative result. See, when it fully went back, you can see the key point. The red is the route truth, the green is the prediction. It's mid-aligned one frame. And then when the ball is fully released, so the upper one is the shock and the target one release. That's kind of, and then you can move to the next one. This one is, yeah, when it go fully up is the key moment, and the stick is fully up. You can look at the head and the two bridge and the stick or the ball as well. They're multiple. So the red one and the green one prediction. And then when the stick hit the ball, it's another key moment. It's admitted by one frame, something like this. And then you have the need for hand. Thing. Yeah, when ball released from the hand. Yeah, one frame is. But then when on the ball up the sky, maybe now, ball start to rub, it's a key moment. Yeah, so it's a predict. And then when the bracket hit the ball as well. So this one, the ball, when it hit, it may be hard to get the object because a lot of time it's just blurry. So it hit. And here it's again the model that fine-tune on pouring. It's just a very small data set. So when the liquid start pouring, the red is route truth and the green is prediction. Stop, please stop pouring just now. Yeah, something like that. So let's wrap up this. Conclusion, what we believe is that space-time semantic correspondence has many potential applications, as I mentioned before. And we actually, in this work, present two data sets and a set of comprehension baseline so that to gain insight about the problem. And we believe that the problem should be approached jointly in space-time, make the problem easier, not harder. And with that, I'm willing to take the question, and thank you very much for your patience listening to my talk. I have a few more sequence, but yeah, I take the question now. Are we on time?
It's fine. Can you just come up here and ask?
First of all, thank you for a great talk. It was very interesting to hear. So I actually have two questions. First is about long-form video understanding. I guess the main challenge would be, for example, if you use transform, as the sequence increases, computational will increase quadratically, right? So did you consider any of those computational burdens when handling those long-form videos? That's my first question.
Yes.
Okay, then second question is, when you're doing spatial temporal correspondence, how important was it to train in the, I guess it was trained in videos, right? How important was it to be trained in videos? Because I think recent paper from Cornell, I think it was called DIFT. They used the vision models to find spatial correspondence.
Mm-hmm.
But even though it was only trained for images, it worked surprisingly well on videos. So I'm curious on how important was it to train on videos? Does it really is spatial temporal correspondence really needed in videos? So those are my second two questions.
Okay. Yeah, thank you. Both are very good questions. Yeah, I'll give you the answer. For the first one, we haven't considered that yet because at the beginning we just want to understand the problem. There's a lot of analysis you can see, like top down, bottom up, component, and many different components. We haven't applied on complexity. Even for the tip editor, it just had to slide a window of like 200, 400 frames and slide them and do it still like computation and heavy tip editor baseline. And then for the second question, I think we may need video training because a lot of time you see motion blurry. And yeah, and a lot of confusing, like something like this one, right? Did you see this one? All this way cannot solve the problem for you because the key point is completely similar when you do low and you up the same ball, only different in the motion direction. Yeah, if you train on image, there's no way for you to solve this kind of problem. But there's many cases like that. And then when you see like playing golf, right? The golf stick even blur, motion blur, and the ball just like go in one line, something like this. And then they need a little multiple frame to predict that correct, not just one frame. Even for one frame, you look by the naked eye, you cannot see the ball. When we do annotation or something, we have to look at multiple frames. to get the small object correct. So that's why we know that what exactly difficult in this problem.
All right.
Thank you for the
Thank you.
question.
I have a question about this second part.
Yeah.
So there are surely video sequences which you cannot establish any correspondence.
Mm.
And it's not at all clear which you can and which you cannot. So for instance, it might be possible to have some semantic correspondence between ice hockey slack shot and a golf shot.
Yeah.
And it might not be possible to have a serve, like a tennis, one of the tennis strokes and another tennis stroke. So where is the, if you made a benchmark, or where would be the distinction between it's a failure of the algorithm or the correspondence doesn't exist?
I think, yeah, a very good question. Have you finished your question or you have?
Yes.
Okay. Okay.
So your examples are sort of like same viewpoint, same forehand,
Yeah.
all are right-handers, all have a decent technique, so they are very similar. So if you have things like get off a bicycle, you can do it at least 3 ways.
Actually, very good question. I think in this work, we assume that the action should be only in the same action, not necessarily the same view, because in the pen action, you will see some same action, but slightly different view. Let's say even for this one, the view is slightly different. Right? Yeah, so not necessarily exactly the same view, but that is the current assumption. But for now, we cannot tell whether maybe that is for future work, but I believe something like if you want to compare similar action like badminton smart with tennis smart, you can accept some correspondence, but it's completely different from like golf with tennis maybe, but the model cannot tell whether they cannot accept it or not. Yes,
Okay,
that's correct.
This is like you are not answering the question, because the deeper definition would be something like the main things can be mapped by just, for instance, remapping the time and remapping the space in some way which doesn't have discontinuities or something like that. So you cannot map, I don't know, if someone, so you say you call it semantic. So let's say it's semantic to say dismount from a bike. And you can do it through like putting the light through the front or through the back, and this couldn't be mapped on each other, maybe.
Yeah.
So maybe you should work on the definition to say what you mean, because then people can think about it. Like, what is the limit of your definition of semantic? I'm not saying you will do it now, because I think the first answer says that you haven't thought about it carefully. You said, okay, it will be an interesting thing. So if I know that it's done, if you have 2 skiers, you want to sort of map the bases in sports, it's very similar, but they are doing very, very similar things. And as soon as people, I don't know, cut things and someone picks the knife first and the forks first and the other way around, maybe you can't do it, because you would have to somehow recut the video.
Yeah, that's the current limitation. Yes. Thanks for bringing it up. Yeah. But I think for now, the assumption is that we have at least a minimum similar semantic levels of the action or similar action. But yeah, and then when it moves to video, the time sequence, like the order of the time, can be also confused more than the image domain. When you have, like in the image domain, you assume that 2 images come from the same object, like 2 cats or 2 dogs or 2 bicycles. You cannot like accept a correspondence between a bicycle and a building, something like that. Yeah, but the assumption is a little bit loose when we come to video, because temporal inherently have confusion when people do the action in different order. Does it like? Okay, thank you. Okay, yeah, we can chat later if you have a question, or we good?
No, nothing on Zoom.
Okay, then let's thank for. Thank you. Does it go well?
Because I didn't have any patterns or something like that, but they're finding the new one and this one gets through. Yeah. Great stock.
Hmm? It's not sharing it in my adapter. Hmm? Why is it? Okay. I have no idea. No idea about that one. Do you have an idea? Just write it.
Linux not good for us.
Yeah.
Video is not, doesn't have any audio. Okay, so this was actually just a pre-recorded talk. They submitted pre-recorded video, but it seems that the audio on this is not really audible. After that, we'll have we'll have the roundtable after the coffee break, right? At 3:15, resume.
How about now? Okay, I think it's working now. Okay, cool.
Is it also showing the right screen? Okay, yay, we're good to go. Yeah, thanks a lot for the invitation. A disclaimer, this talk will not be about tracking whatsoever. So you might, if you have some other tracking talks you want to visit, maybe, So I'll be talking about segment anything. This work was done in Meta AI with wonderful folks in our team. So 12 people research team, as well as a large set of collaborators that really helped us to make sure we can collect the data on the scale we wanted to collect it, and that helped with the demo that I think was the important part of this project. Okay, so I don't know if you know, but until very recently, computer vision was not accessible for a practitioner, right? I'm giving a lecture set to natural scientists. I'm talking about like how great our recognition models are. And then, I'm talking about Fosterson, Muscarson, and all this stuff. And then in the end, an ecologist will come to me and ask, okay, sure, I'm counting trees in California. This is important. We don't want to more fire. How do I use your models to count trees? And well, my answer is like, you cannot, right? Basically, you will need quite a substantial budget to annotate the trees. You'll need not a fantastic expertise, but some expertise to know how to train these models. And then, yeah, you will have your tree counting system and it will work pretty good. But at this point, you're already not an ecologist, you're a computer vision PhD student. So in a lot of places that companies can afford it, they do it. A lot of computer vision is basically inaccessible. So, and this is due to the way we were treating like our tasks. Basically, we took deep learning machinery, we took task X, and we tried to achieve this step change on a specific task with a specific data distribution. Like in the last decade, our like COCO numbers have doubled to even tripled. Like on COCO, we're crushing things. At the same time, if you want some adaptation, if you're going away from 80 categories in COCO or in a different image domain, you'll have troubles and you will need to adapt. You will need new data. Thankfully, in the last few years, we see the emergence of so-called foundational based models. And the trick now is take this kind of models and apply all of them, some subset of them to the other tasks. So here, the goal is to have a step change on the broad task for broad data distribution. And most crucially, the adaptation here hopefully can be done without parameter updates. So purely from prompting. In this case, hopefully there will be more people that can use the same technology. Okay, so I'm working in segmentation. So let's try to apply this new paradigm to segmentation. What would it mean? It would mean to have a segment anything model, a component that broadly solves segmentation, that can be useful both as a humans directly, but also as a component in a bigger system that can be used for different tasks and new domains, and that can be adapted through prompting. Okay, so let's say we did it, but segmentation is quite a niche problem, right? Like if we're looking at LLMs, we see that they're able to solve so many needs that people have. Segmentation is a narrow problem. At the same time, we released our model only 2 months ago, and we can see that people started to use this ability to segment in a broader, like on a broader image domains everywhere. Basically, we see some applications in science and medicine where people show that segment anything is actually working better than brain extraction methods. With a geospatial data analysis, we see that it's very useful. At this point, segment anything is incorporated in most of the data labeling platforms. People show it as a component to get to 3D objects, and also various applications that use segment anything as a part of it. For example, caption anything, in paint anything, track anything. We see the works that use them as a component. And finally, we did ourselves, but in general, I hope that people will use segment anything to create new data sets. So as we can see, with like 8 billion people, even the niche thing that just focuses on segmentation is quite useful as soon as you get to the point there. It starts to work for different domains and a broader, generalizes in a broader sense. Okay, I hope I convince you that this is important to get to the points there. Our model generalized well. So how did we do this? The segment anything project goal is developed a promptable model, pre-train it in a broad data set using a task that enables powerful generation. At this point for segmentation, none of it exists, right? The promptable model for segmentation, not clear what is it. Data is not broadly available on the internet, unlike language data. So we need two solutions for all of them. At the same time, they're all quite coupled. And that's what we're trying to do. Basically, we come up with 3 things with a promptable task, with a model, and with a way to collect data. And I'll talk about each of them in detail next. First, promptable segmentation. What we do, we want adaptation through prompts. So we're taking the idea of prompts from NLP and apply it to segmentation. What is a segmentation prompt? In general, it's anything that specifies what do you want to segment. In our case, we use the simplest possible prompts, for example, a foreground and background points, or click at a thing, say I want segmented, boxes, masks, or even text. And as a result, with this kind of prompt, our task is, given an image and the segmentation prompt, we want to get to a valid mask. Why prompt segmentation? And I will explain why valid mask is also important in a second. So promptable segmentation allows you to use segment anything model in combination with our model, so as a component. It's also very easy to simulate during training. If you have a mask, you can easily simulate points or bounding boxes. And then crucially, because segmentation data is not available on the internet on the scale that we want, it also enables human in the loop annotation, which we will use. Lastly, why valid mask is important is because in many cases, the prompts, and especially the simplest prompt like point, is actually ambiguous, right? Let's say I'm clicking on the beak of this bird. Do I actually want just a head? Do I want a body? Do I want the whole bird? It's not clear. And if you don't pay attention to this thing and use the losses as we would usually do, it will inevitably lead to mod averaging. And basically we observe it at optimal model. If everything is perfect, the optimal model will do mod averaging. So we need to come up with something special that will disambiguate it, as in the end of the day, you know, we want it as a component and system, right? Here there is a gaze detection, and we want to get to the mask. If there would be a mode averaging here, it wouldn't work as nice. It wouldn't be able to select special objects. So in this case, even if the prompt is ambiguous, the model needs to produce the reasonable thing and not the average of several reasonable things. Okay, so I think I motivated the promptable segmentation tasks. Let's go to the model, which we call SAM. It has overall 3 major components. It's a prompt encoder. It's an image encoder, which is the heaviest part of the model. And then a very lightweight mask decoder that converts this prompt and image features into a mask. In more detail, given an image, we first run image encoder. This is a simple transformer architecture adapted for high resolution input. And then given this image embeddings and a prompt, which we run through a prompt encoder, we have a mask decoder that gets us 3 predictions or 1 prediction, depending on at which stage you're using it. So what's important here? The important part is that the conditioning on the prompt is happening only on this side, right? That means that the image encoder, it's a huge model, but it can be run just once. In many cases, it can be pre-computed. And then this part, the mask decoder and prompt encoder, is actually significantly it's significantly smaller. So it's actually so small that we can run it on CPU on a web browser. And that means that we can use this kind of model for annotation on front end without having a cluster of GPUs working behind it. So that makes the annotation platform and work with annotators significantly simpler. We can scale it up whenever we want. We can scale it down. We don't need to we don't need to work with a complex machinery. And in the end, like what's important here to figure out the ambiguity, our model is able to produce not just one mask, but it's actually producing several masks, 3 in this case, and the score, IOU score. So components like prompt encoding and image encoding are fairly straightforward. With mask decoder, our goal is to create the model which will be as simple and as fast as possible. So we started with a standard transformer decoder that is used in detection transformers and mask former and other previous works. But here, in addition to prompt attention and prompt to image attention, we also add image to prompt attention. So there are 3 different attention layers. Note that image to prompt attention has the same complexity than prompt to image attention, because we have just a few prompts that makes it quite efficient. And MLP is run only on prompts. We cannot afford to run MLP on image embeddings. It will be much slower. In the end, we just produce K masks, and this thing is very fast. This is the main component. This is the main goal. Is it producing the very high accurate masks? No, it doesn't. But this is the trade-off that we need to make sure that it's fast enough. How do we train? So first prompt is likely ambiguous. So what we need, we predict 3 different masks. We compute the losses for all of them, but we propagate only the one with the minimal loss. So here, this is the simplest possible way to handle the ambiguity case and the mode averaging. So you allow the model to predict different masks, and then you do not penalize it for predicting something that is not your ground truth. And if at least one of these 3 masks is good, this means the model is good enough. And we see that this very simple solution is good enough to disambiguate the predictions. And we see that mode averaging, that was a real problem for us, basically disappears. After the second prompt, generally the prompt is not ambiguous. So we just predict 1 mask to save computation. Finally, as a loss, again, very standard for most of the image segmentation, we use a combination of focal loss and dice loss. Okay, so this is the training, this is the model. What do we need the data to train this model? As I said, the segmentation, unfortunately, is not abundant on the internet. So there are existing data sets, but they're incomparable to what other base models are trained on. So in this case, we decided to basically brute force this problem. Given our model and our ability to annotate data so easily without need of GPUs or anything during the annotation, we try to do data engine that will do model on the loop data set construction. So yes, we already have SAM that runs in amortized real time on CPU and browser. So we just went for it. First, the annotation has 3 different stages. And let me show, here, yes. So this is the example of the internal annotation tool. This is me annotating in real time. So I just click at things. Sometimes it's not perfect, so I need to fix it. It's still not perfect, right? It's not pixel perfect, but we know from our experiments in Coco that it doesn't matter. Deep learning methods right now, they are able to generalize over non-pixel perfect masks, producing much higher quality masks overall. So this is the quality we're looking for. And as you can see, quite fast, I can annotate many things. So this is what we start with. We collected that way 4.3 million masks. This is much faster than polygon-based Coco annotation. And during this collection of manual annotation, we retrained our model. As soon as we get more data, we retrained this model, and we will keep annotating. So we saw that every time we retrain the model with more data, we actually get better and better performance. The annotation time gets down. At some point, though, we noticed that our internal metrics weren't going up as much. So we went to the second stage of the pipeline, which is a semi-manual stage. So here the goal is increase the diversity beyond most prominent objects. The thing is, even though the images are all different, the annotators start to look at them, they salient objects, and images that photos that people make. So it will be cars, buildings, people. So it will be the same things again and again that annotators were annotating. So our goal was to increase the diversity. For that, what we did, we just took the data that we collected so far. We trained faster CNN model. We run faster CNN model on to predict the boxes for these objects. We run it on new images. We ran SAM on top from the boxes to masks, and we gave it to the users. I said, don't fix them. This segments might be bad. Don't fix them, but annotate things that were missed by this object, by this system. So as a result, we were able to keep increasing the diversity of our masks. We added another almost 6 million masks. And at this point, we were still retraining our model every time we got substantial amount of masks. We were scaling the model and we were getting the ambiguity, disambiguation to actually work. Finally, once we get our disambiguation work, so if I click at the caret here, it will be a caret and a whole bunch of carets. We were able to get to our fully automatic stage. So here we run SAM in so-called segment everything mode. So what does it mean exactly? We just get a grid of points and we make our 3 predictions for each of the points. Now we have a whole bunch of masks. We do non-maximal suppression and we have a lot of masks here. So no manual annotation whatsoever. We run this thing on 11 million images, and that way we generate more than 1 billion masks. Are these masks any good? Of course, there is no way to check all of them. So what we did, we just sampled some of the masks and we asked annotators to improve them to get to pixel perfect masks. And we estimated that 94% of them have at least 90% IU with the fixed masks, pixel perfect masks. So this is somewhere in the ballpark of existing manually annotated data set. So we have some guarantee that our data set is of good quality. At the same time, it's 400 times larger than any previous segmentation data sets. Here, some examples with just a few masks going to some ridiculous number of masks here. Okay, so we have everything now. We have a task, we have a model, we know how to train it, and we have a data set that is big enough to train. We did it, and now the experimental part. So with experimental part, what are the expectations here? So we want to see its broad applicability, and we want to see good performance on the tasks that it was trained on, mostly the single point valid mask evaluation. But then also we want to see how it's applicable to all different segmentation tasks. And here, this edge detection, object proposal, instant segmentation, text to mask, it follows more or less the development of the segmentation field itself, right? More than a decade ago, we started with edge detection, then we moved to proposals if the field was maturing, and so on. So here with experiments, we're also following the same path, but we start with single point valid mask evaluation. What we're interested in here is how broad the data sets, the domains that we can handle with our model. So we took 23 diverse data sets. Here you can see microscopy, you can see underwater imaging, X-ray imaging, night vision, fisheye images, and so on. And we just tried our model on them. What's the evaluation protocol? You take a ground truth mask, you sample a point from the mask, you prompt our model with this point, you compute an intersection of union, and the metric is mean intersection of union of masks. Note that our model can predict 3 predictions. So in addition to our standard prediction that just take most confident masks out of 3, we also do an oracle evaluation where we take our best mask. So this is not fair, but at the same time, given the data set, we don't know the biases of the data set. If there is a plant and you can annotate the whole plant as a mask or each petal, we don't know which one do you want. So at the same time, our most confident prediction might be wrong from the view of this data set. If you take the oracle evaluation, you can see, okay, does the model have among 3 masks, one of them? Okay, so we're comparing our model with Rhythm, which is at that point was the best interactive segmentation model. And we see that quite on a few data sets, we have much better performance. We have few data sets that we're worse. At the same time, if we're trying an oracle performance, we see that everywhere we're better. In particular, we see a big gap in this data set, GTEA. What this data set is, it's a data set with segmentation of hands. And what our model is doing, if you have one click at a hand, it will segment both hands together. At the same time, this data set is annotated as hands separately. So that's why the Oracle evaluation, our model, in addition to the most confident one, which is 2 hands, it will also predict just 1 hand. But that won't be the most confident. So this is a troublesome evaluation. So in addition to that, we also did a human evaluation. We took a set of data sets. We gave a point, we gave the mask, and we asked annotators, okay, is it a good mask given this point? And here we see that our model is significantly better than written. And in many cases, it's very close to ground truth performance. Also, you can see here that disambiguation is very important. If we just train SAM with just single output, we see that performance is quite much worse. Okay, so now going through the history of computer vision, how to do edge detection with prompting. Our prompting for our model, we just segment everything. We filter edges from the masks that we predicted, and we do the edge NMS, which is a standard approach for edge detection. So here we see that the precision-based metrics are slightly worse than the best edge detection methods, the holistic edge detection, quite old, but very good method. At the same time, our recall is almost as good, sometimes better. Then you see examples, you can see what's happening basically, because our model has no biases on what kind of data set this is. We're trying to segment anything. Our model will try to segment each, and it's hard to see here, but it will segment each window as well, and annotators won't segment it here. So this kind of thing pushes our numbers down, but I would say the edge detection is still working with this method. Another example is object proposal. Again, we use a segment everything mode tuned on to produce more masks because this is what recall wants. And as a baseline, we use a strong BIT baseline. Here we can see that for medium and large objects and for common and rare objects, our model that never seen this data set, this is ours, actually performs better than the model that was trained on this data set. So if you have a case there you don't have enough data for your specific instance, it might be better to actually use our model than a model that was trained on your data. Next example is instance segmentation. There we use SAM on top of bounding box detection. There we see that performance is quite much worse than the not state of the art, but quite a solid system. But at the same time, then we'll look at our predictions. They look pretty good. So what's happening here? And again, our model doesn't know the biases of the data set. So for example, Coco and Alice, there will be no holes in the segmentations. This is just the way the data set was created. And the model that was trained on this data set knows it. In case of SAM, it doesn't. So given the click on the plate, it's totally reasonable to segment just the plate. But your IU will be worse. So we again run a human evaluation, and we saw that this actually performs better. And humans, given a box and a mask, humans prefer our segmentation to VIT that segmentation. Okay, finally, we have some preliminary results with text-to-mask experiments. So here as a prompt, we want to use the text. Unfortunately, we don't have the data, right? We don't have a huge amount of paired text and mask data, but we have a clip model that is aligned between image and text. So what we can do here, for training, we take each mask and we compute a clip image encoder embedding for this mask. Now we prompt our model with this embedding, and we train it that way. So during training, the model haven't seen any text whatsoever. During inference, we use text. We use a text clip embedding, clip encoding to get the embedding, and we use this as a prompt now. Thanks to the alignment inside the clip, this thing actually works. Here are a few examples. So that it works with a simple example like a wheel. It also can find more complex things like a beaver tooth grill. At the same time, it's not perfect and it's really just preliminary results. So a wiper, it fails, but a wiper and a click on a wiper, it actually works. And finally, it's important what you use with words. So here, for example, wipers and the same exact point, it will give you both wipers at the same time. Okay, so I'm done with experiments, a few oblations. Once we collected the data, we try to see if less data is good. And we see that 10% of the data is almost as good. There is still some improvement, but it's not very large. So I would say if you constrain in the storage, you can use 10% of the data as well. And the reason here I feel this improvement is not as good is because our data set is constrained on the scene level, the same kind of images. Even though there are many images, most of them are the same. So the masks that we're getting, they're very similar. So if we could expand our data sets to different kind of domains, that would be better here. And I would expect the plots to be more exciting here. With the scaling, we see some improvements, but as soon as you go beyond VAT large, the improvements is quite not very good, I would say. We try to go further, and there's still some improvements, but they're not exciting for us, unfortunately. Okay, so some limitations very fast. Mostly the limitations here, our model is not pixel perfect. And this is a trade-off that we had to do because we wanted the model to work for the annotators. That means it should be fast, and the communication between image encoder and the decoder should be tiny. So this feature should be small. There is a recent work with HQSAM that actually rectifies this problem. But in their case, the embeddings that are going back and forth are actually pretty big. So you can solve it. It just in our case, it wasn't. It was a different trade-off. Then interactive only models works. Interactive only models, the models that are focusing on interactive segmentation, works better with many points. That wasn't our focus. We only amortize real time. We still need to run the ATH. So if you want to run it on video, that's quite costly, at least with the ATH. Text to mask is only preliminary. Finally, if you have a domain-specific tools, for example, for biology, for cell segmentation, they're likely much better than our tool. Final conclusion, the main contribution here, as I said, the new task, the new model, and the new data set. What we try to do, we try to attempt build a base model for segmentation. If we succeeded or not, this is up to community to decide and its usage. And we still think that, adjust the segmentation. So there is a big question. What will it be for bigger computer vision? What kind of model we can tell that is not just a foundation model for segmentation, but foundation model for whole computer vision. That's it from my side. There are links on the project page and interactive demo. Please try to play with it. It's quite fun. And yeah, thanks a lot for listening. Thank you.
Questions from the audience, and if you how you can approach the microphone and Adam is asking.
Hey.
So beautiful paper. I used it. I like it. I wonder what to do with that data set though. So it's 11 billion images and it's outputs from SAM. What should I do with that?
Well, the world is your oyster. So yeah, I mean, like this is the data set. Our method SAM is self-hosting method, basically. There is no difference between model weights and this data set. So you can actually completely forget about the weights, use this data set that we released to retrain the model, and you will get the model with the same kind of performance. This is the use of so this is, if you want, is basically a different representation for the same thing. What can you do with it? I don't know. It's really up to you. We hope that people could start to, we showed that you can use clip on top of these things. So like this is how you train text to image embedding, right? Like in general, you could run, you have SAM, you have access to these images, you could run it yourself, but this is quite costly. So basically we did this job for you now, and you can run clip models if you want on top of them. So, but again, like, I don't know, you will need to figure out your own papers.
Of course, amazing results, and it's not a project. One of the things I find interesting is the way that you frame it, and sort of what's trying to annotate is focus on the visible pixels, right? And I'm kind of curious if you have thoughts or ambitions towards models that more generally reason about not just this is strictly visible mass, but also, yes, there's partial inclusion, but we can infer the regions that are included as well.
I feel like all my answers will start with I'm sorry. Like this is what we embarked on, right? We wanted to prompt to also tell you, okay, I want a visible part. I want to so model and model segmentations. We did not succeed. It's hard. So please do it.
No, it's definitely going to be but I think it's
Thank you.
Thanks again for the wonderful work. I think it's not to apologize for it's really wonderful. I really like the part about the task agnostic sort of or task agnostic segmentation, or like let's ignore what objects are, let's ignore what's the campus sort of focus on just perceptual movement. But at the same time, you have the whole ideas with like Gestalt, where like this can help you, like knowing the five edges of the star, you can infer the star. Can you comment on like what are the trade-offs here, or if you think like no, actually the way to go is maintaining a being agnostic towards what the task would to us, or if at some point we should go back about the priors, about completion or all the things.
Yeah, I absolutely think that we need to think about these things, right? Like this is the model that can segment anything. No one needs anything. People need the thing that they care about, right? It's very hard to get the thing that you care about from this model at the moment, right? So in order to do this, you need to do something on top. And like, we get into these models that can do anything in the vision. I'm not sure this will be part of it, It might be a part that will generate the data for this kind of some subset of the data, but it unlikely be the thing that if you more knobs and we get to a proper vision system. So I completely agree this is important, right? Like you want to name things, you know what you're interested in. It's not just anything. So yeah, like going forward, we need the knowledge graph and we need to understand what we're looking at. We're just not there yet, unfortunately. I'm sorry.
Yeah, thank you for the wonderful talk. I've been using SAM for some of my personal research and it's working quite well. I have more of a specific question on the model behavior. When you prompt SAM like with multiple points, you can segment what you wanted to. But I've often noticed that if you segment everything more, it does really well at very small objects. Like it can segment pebbles and everything, parts of the body and everything. So I also noticed that in the data set, let's say there's a person, it has separate masks for the hair, face, and body, and shirt, and everything. So it does really well at small objects. And do you have any intuition on why it prefers smaller objects over the larger ones?
I think that's just a bias in the data. There are significantly more small objects. If we're talking about Pascal VOC, most of the objects are big. We're going to Coco, it's shifting. There are significantly more small objects. We're going to Elvis, it's shifting even more. So if you want to segment anything and you need a data set with all of them, the number of small objects will be incredible, right? And if you don't care about the classes of them, they will dominate basically the picture. It wasn't a problem for us until very end. Basically, if you click at the raspberry, it will give you the whole raspberry. But at the very end that we collected all this automatic data and we train it, we figured it will be a raspberry, a bunch of raspberries, and the whole bowl of raspberries. This will be the three answers. But after we train the model and we train it again, it would pick the smallest thing will be a cell. And what are those? Anyone knows cell on the raspberry? I don't know. This thing will be the smallest thing possible. So right, the bias towards small things increased a lot. So I think if you really don't care about small objects and you care about bigger things, you will need to retrain and be very careful and what of these masks you're actually using.
Starting from the first stage open analysis, identify over the retraining steps.
Yeah, but now you have this data set and you have plenty of big masks in it. It's just how you train. If you can retrain our model again, and the retraining is not that expensive, what the data set creation was expensive. This thing you can try to do again. Thank you.
I wanted to ask also about the segment and everything mode, where you go from the prompted mode into something which can be called automatic. So my understanding is that the output is a partition of the image. No.
Yeah.
So when you show, so then when you show things, you show a partition, or how should we read the output?
It's too much too, sorry. It's a set of masks, basically, a set of masks plastered on each other. Yes.
What are you actually showing? Because as some pixel you might have 10 overlapping masks.
Yeah, I'm just plastering them over, like starting from the largest mask to the smaller mask. That's
And
what I'm
it's
showing.
like let's say like this, a buffer, or is transparent, or so we see this. So what we see when you show this is the smallest mask at the pixel.
Yeah. Well, there
might be loads of masks beneath which we don't see.
Yeah, exactly. Like the thing is, like what you care about here, that like boundaries are all aligned, right? Like if you would have a boundary like in the middle of the object, you're like, okay, something is going wrong, right? But yeah, you don't see here the union of the objects. And in general, we don't have as many union of the objects, but for a person, you'll have a jacket, the t-shirt, and the whole person as well, but you cannot see the whole person mask, right? It will basically be occluded.
So I think you figured out that from the set of masks, to make it look nice, it's good to show it in a way that you start with the largest and the resulting thing is pleasant. But
Yeah.
if someone wants to, what one gets is the set of masks, and then it's his job to somehow figure out what he wants.
Mhm.
And now in this segment everything mode, you start from every pixel.
From a grid of like, it's quite expensive. So
That's
we do 32 by 32 grid. You can do
okay,
anything else.
That's what I thought. So that probably defines the smallest object you can get. So it's more or less, I'm thinking that whether, okay, I'll use the word where this is not a gimmick. So mainly this is a tool for prompted things. And when you want to do something which looks like fully automatic segmentation, it shows something which looks like a standard segmentation output, which would be say semantic segmentation, a partitioning. Every pixel gets a label, but you get something much more complex,
Yeah.
which is visualized in a way which looks the same
Yeah.
as the normal thing, but it's
Yeah.
So for instance, what would be the average number of masks output per pixel?
Good question. I don't know. The statistics that is related, if you have any random pixel with 50% chance, it will be covered by more than one mask, right? But actually,
there's also a sort of, so that's,
I
didn't even consider that. So there are some pixels which have 0.
they might, yes. So I actually
So
like very,
the 0 labeled pixel, so it's like no label is given to less than 50% of pixels.
no, if you pick the mask, you pick a random pixel on this mask, then with 50% chance, there will be another mask that cover this
Okay,
thing.
so it says that, so I will translate this, at least 50% of pixels have look more than 2 masks.
Mhm.
And we don't know the number of 0, and we don't know the average.
Mhm.
Okay.
Unfortunately, yeah, I don't.
Okay.
But like, I'm really glad you touched on this, because like like I was lying to you. Segment everything is it's a good name, but it's actually like, you don't want segment everything. What you're saying, like, oh, but this is not what, like, this is like, I gave you what you asked for. It's segment everything, and now you're complaining that it's not what you wanted. The thing is that segment everything is not a really useful task, exactly how you pointed it, right? It's too many, like, imagine I'm talking with you right now, what I'm interested in, people, right? If I would, interested in a clothes, I would need segments of clothes. If I would be interested in your hair, I would need like counting each hair separately. So in the end, if I'm trying to segment everything, you will end up with a pile of things that are basically piling on top of each other, that like you will need. The problem that you have afterwards is almost as complex as the problem you started with. So prompt way, the conditioning is the thing that we did here, right? Segment everything is a way to get, like, you want edge detection? Here, we can do edge detection for you. You want edge, like, proposals without any prompts? Sure, we can do it. But at the same time, this is not everything, and moreover, you don't want everything, basically. We started with everything.
You brought it up. I wanted to leave, but now you brought it up. When you said it, for the edge detection, you didn't use the segment everything mode, because there you would have a whole forest of edges, or you had to somehow
No.
But you do, okay, so this was hidden under the word non-maximum suppression.
Wait,
So now we have a pile of regions that overlap.
Yeah.
They will create lots of promiscuous edges. And so these are edges from all the, so something must, so first we have segment everything, then we have every edge on the, let's say, on the side, on the border of every single
oh, every
segment.
single mask, yes.
And then something has to happen to get this, otherwise it would be a mess of levels. And this operation is very interesting.
Just like, and then you go to like edge, like NMS from like Piotr Dollar 5 years ago.
Okay, so the operation is add and.
Yeah, this is like, it works with like all these methods, any edge detection method through the centuries, basically use the same NMS technology. So we can show things without it. It will actually look distant. You know, our edges there are a lot of edges, but they're always pretty much in the same place, you know? So we need the edge smoothing to fight with the metric that is here, you know, that does one-to-one matching. Like, if you read the paper, we have all these details there. It's actually, I'm very proud of our paper. You should read it.
Thank you for the excellent work. So my question is kind of answered already, but I still would like to ask. When it comes to text to mask, what if the text prompt is visual question? Did you test the performance of visual question answering visual grounding for visual question answering?
So as I said, that like results there are really preliminary, so it doesn't work that well. Like we see that there is no reason for it not to work. So there is a reason. There is a domain gap between image encoder and text encoder still, right? We don't see any fundamental issues with it. We just weren't able to push enough. So the results, like we didn't even evaluate anything basically. So the answer is I don't know. But like from what we saw, basically, it works in many cases, but not enough to, you know, to claim that we like, you know, that this thing now works, text to mask works.
And the second question I would like to ask is related to some specific visual attributes. But this question might be already answered by the previous askers. Yeah. So for example, if when it comes to some document analyze when the model is required to segment some text. So I'm not sure how it would work for very specific detailed visual attributes rather than some humans.
Yeah, it won't like, so like if you need some special education to segment an object, so like for example you're a radiologist, this thing will not be able to use it to do it, right? Like segments it can provide is a very simple segments that like will like a person recognizes as like, okay, geometrically that seemed like a segment, you know, a stripe on your shirt can also be a segment, you know, from this point of view. But if it needs some special education, this model will not be able to do it. So there are like limitations in that way that are very clear. Thank you.
With some encouragement of my neighbors, I think segmentation models like that had lots of problems with things like texture segmentation. So look at my shirt, and I could be on a background or a wall where someone like sprays dots. So here it will go probably to the texture level. Or have you seen like what happened? Look at this carpet, like lots of stripes.
Yeah.
So it will not try to create like the classical texture segmentation would say like, okay, you might have two types of cloth and it will separate into two regions. Probably this will go to the lowest level sort of uniformish thing.
Yeah. Like if it predicts a few, like it has this ability to predict a few things. So it will likely predict as small thing as possible.
Yeah, so like look at these chairs. And so if someone wants to deal with repetitive texture like classical, they would have to deal with that at some other level.
Yeah, absolutely.
Okay.
Thank you.
I have a quick question. So you touched, just to keep us on time, this will be the last question. I think we're gonna have to. You.
But he's here and you can probably. No,
So you touched on the density bias in terms of wavelengths, and you touched on how the model changed its bias in terms of the masks in the end. But how were the images collected themselves? Like you showed that the generalized data sets and the out of domain, what is the bias of the images in that data set?
So, like, in order to release the landscape is very hard. So we had to like search for the images that we will be able to actually release. And we found a provider for these images. And this images as everyday scene level images, right? They're across the world, and we have some analysis of like how diversely they distributed in the world. But this is the usual photographers. So there will be no X-ray images, no medical images in it, nothing like this. So it's everyday scene level images. And I think this is the big limitation of this thing, right? Like there are actually more indoor images than outdoor images. Other way around, more outdoor images than indoor images. People do like to make photos outdoor, right? And it's scene level, right? Like if you like, the proper way to generalize would be to have images from all possible domains. But here we have this limitation that like, this is the only data we're able to annotate, unfortunately.
So you're saying it's more like internet images in general?
Like people can upload this kind of images in the internet, and a lot of people do.
Okay, this was the last question. Thank you for your talk.
Thank you.
Okay, the last talk from the Zeynep Akata, and she is our last invited speaker, but she is unfortunately couldn't attend the CVPR in person. She lives in Germany, and because of the time conflicts, she couldn't come here. Maybe I could, yeah, we will just listen her pre-recorded talk, and she will be talking about the explainability in deep learning throughout the communication. Before starting that one, the people in the Zoom, the audience in the Zoom, can you hear us? I think so. Yes, they can hear. Okay, here we go.
I would like to thank the organizers for inviting me to give a talk in this CVPR workshop. I'm going to talk about our research on explainability in deep learning through communication. I'm a professor of computer science at the University of Tübingen. I'm also affiliated at the Max Planck Institute for Informatics and for Intelligent Systems. I will be talking about only a part of our research on explainability and the part that involves communication. I will also talk, maybe I give you an outline of my talk first. I will mention how explanation and learning are related. And then there are many different ways of doing explanations, of course, but in our in this talk, I would be talking about explanations that are broad, simple, contrasting, and abstract. And these are achievable through very easily through conversations. Then I will argue that explanations should be tailored to the communication partner because our communication partners could have different understandings of the world. So we need to tailor our communication channel for them. And then I will summarize and talk about future research possibilities. Okay, so let's talk about how explanation and learning are related. I think the best way of explaining this concept is by an example. And here I borrow the example of Tanya Lombroso from her Trends in Cognitive Science article from 2016. She says there are two different types of aliens. One of them is called Glorp and the other one is Grant. And as you can see, their heads are different, their body shapes are different, their color distributions may be different. And based on these differences, we are going to create a classifier that is going to classify them, the Glorps versus Grants, as best as possible, as highest accuracy as possible. We might group them according to the shape of the head and say that all the square-headed aliens are called Glorps. And this will be a classifier with 75% of accuracy, which may seem quite high. But of course, this classifier makes a classification decision based on the wrong reasons, which could be quite problematic when it comes to generalization capabilities of this classifier. So we go back to our learning problem again, and we try to look at other properties that could be discriminative. For instance, as we can see, the shapes of the feet are quite different. And if we group the aliens based on pointy feet into the same group, then all the Glorps would be grouped into the same cluster, and the classifier will be very accurate, but also the classifier will be making the decision based on the right reasons. We are looking for explanations of this sort. As Tanya defines them, these explanations need to be broad, simple, and contrastive. They need to justify a broad range of observations. They need to be simple, and they need to provide a concise description for the communication partner. So here comes the importance of the communication partner. And then they need to be contrastive. They need to differentiate two alternative decisions. We need to be able to argue why a class does not belong to another one, why an image does not belong to another class, for instance. So based on that, we could in fact use language for such communication, for creating such simple explanations. And for that, we have created this data set using the images of birds and flowers data sets. We asked Amazon Mechanical Turk users for annotating our images, and we asked them to mention at least 3 different properties and at least 10 words for per image. We annotated every image with 10 sentences, and in fact, this data set has been used in many different ways for generative, for image generation as well. But what is the difference between an explanation and a description in this context? We would like to define these concepts based on class relevance and image relevance. So, a description, let's look at two different images first that come from 2 different bird classes. The first one is Western Grebe, the second one is Lichen albatross. And the description says this is a large bird with a white neck and a black back in the water for the first class. And for the second class, it also talks about the water because these 2 birds are water birds. They are oftentimes found in the water, but this is not necessarily the reason for classifying these images. Even if they don't appear in a water background, they should be classified correctly. So a description is not an explanation. A definition talks about the Western grid with all of the discriminative properties, and these properties may not be visible in the image. For example, the belly of the bird is not visible. And then for the Lytham albatross, again, the belly is not visible, or maybe the feet are discriminative properties that is also not visible. So in terms of class relevance, definition is very high, but in terms of image relevance, it's very low. We are looking for visual explanations that are both image and class relevant, which means the sentence needs to talk about the class itself. So it needs to talk about the class specific properties that are visible in the image. This is very important. Now I would like to talk about how we generate these broad, simple, contrastive, and abstract explanations. Let's say the task is as follows. There is a user who might have partial observation about the environment, and then the user asks questions like, what type of bird is this? And the computer, the model, needs to look at the image and classify it. It's a cardinal. And then it needs to justify the classification decision, because this is a red bird with a red beak and a black face. In fact, to improve the image relevance of the explanation, it needs to point to the evidence for this. Red bird needs to have a bounding box surrounded by it, and so on. I also mentioned that explanations are contrastive, so the model needs to say why not. The user might ask why not a vermilion flycatcher, and then the model needs to think about how a vermilion flycatcher looks like. What are the properties, the distinguishing properties that are not visible in our original image? Like black wings are not visible in the cardinal image. So it talks about the black wings when it needs to justify why it's not a vermilion flycatcher. In this article, we achieved that by taking a model that looks at the image, extract an image feature, and also makes a classification decision. And then a language model takes these image features and classification decisions, and makes use of it while generating the next word. So it is a class and image feature conditioned language model. Then we generate these sentences, and these sentences then get split into attributes, into noun phrases, using a part of speech tagger and an attribute chunker. And then an explanation grounder that has been trained on a different data set, because this data set doesn't contain bounding boxes, needs to find matching bounding boxes for every noun phrase. For multiple sentences, we do the same thing, and then we have a phrase critic model that ranks these sentences based on how well every noun phrase and bounding box match is scored. So it looks at the cumulative score of the sentence and says this sentence is more suitable for that image. Doing that, using bounding boxes or the visual evidence of the mentioned phrases improves the generated explanations, in the sense that, for instance, for this red-winged blackbird, it talks about red spot on its wing bars, because this has a very high score in terms of bounding box and phrase matching. And mentioning this gives a high score for the sentence. So it becomes more accurate, the sentences, forcing this grounding property. This has been shown also in human studies. Then I mentioned that the explanations are contrastive. So we show this image, we ask what this image belongs to, which class this image belongs to, and why not another class. And we did define this other class based on looking at image features or image similarities between this image and all the other classes in the data set. And we find that this image is one of the closest images to our original image, and the class of this image is red-faced cormorants. And we decide on the most flat bill, the counterfactual property, the contrastive property, based on how well the class discriminative properties of this alternative bird get scored when they are projected onto that image, onto the original image. It seems long flat bill property has one of the lowest scoring bounding boxes for this image. So we choose that as the counterfactual phrase and say because it doesn't have a long flat bill. Then I would like to talk about how we generate abstract properties, abstractions of these explanations. And in this work, we again make use of language as the communication channel. And we say two models will be communicating. One of them has an idea of which classes this image might belong to. And the second model looks at the image and can answer all of the questions about this image, but it is not allowed to answer all of the questions. It is allowed to answer only the question that it is asked. So the task of this agent is to come up with the right questions, and the task of this agent is to reveal the answer of that question only. Then so the first question is it furry? The answer is yes. That eliminates two of the classes. Then this remaining classes defines the next question. And also, as a byproduct, we have a decision tree. We construct a decision tree because now, based on this property, all the other classes can be ignored. The next question is, does it have whiskers? The model says no. And then this already determines the classification result. It's a dog because this is the only remaining class in this case. So this way, in this work, we are trying to generate simple, broad, contrastive explanations that are also abstract representations of the object. And while doing that, we want to improve the transparency of the decision-making process. We have two agents communicating with each other. The recurrent decision tree agent that has an external memory and uses LSTM units to keep track of the gameplay. And then we have an MLP that determines the next question to ask. That's the question that maximizes the classification score. Then the attribute-based learner agent takes an image, extracts features from them, and based on these features, it can classify the image based on all of the attributes, whether this attribute is present on it or not. But it won't be able to reveal the answers of all of the other questions, but only the question that it has been asked. That determines in some cases, the next question, in this case, the final decision, because that eliminates the remaining one class. In this work, we were trying to make use of these simple representations or abstractions as an information bottleneck for the classification decision. Still, the classifier is actually a black box deep learning model, but because we use this information bottleneck, we can make the actual decision-making process a bit more transparent. In which cases would this be useful? For example, we have two images. We don't know if they belong to the same class. We start asking questions. Well, does it have white underparts and so on? Up to the point of black wings, these two images belong to the same bucket. They fall into the same bucket. And in the black wings property, they split. We see that the first image gets classified as a blue kingfisher, which is wrong. But the reason seems to be that the black wings property is not correctly detected. And this is actually justified because the bird is flying and the black wings are not visible. Another interesting observation we had was when we looked at two different images that belongs to the same class. One of them is a female bird, the other one is a male bird that has black head. And the classifier thinks that the black head, the black crown, is a class discriminative property for this class, which is wrong. In all the male birds of this species, it is correct, but for the female bird, it is not. It seems at this point in time, the classifier has learned to classify these objects probably correctly many times, but for the wrong reasons. And this we can call it in this way. When it comes to object abstraction, we may not have access to predefined vocabulary, or we may not have access to attributes like I described before. So in these cases, our aim is to come up with a vocabulary that is universal. For this, as a simple proof of concept, we use human sketch or sketches that are made by humans. As you can see, all three of these sketches, they correspond to the same class, but they are drawn very differently. And because of this reason, oftentimes these get misclassified by classifiers. So what we would like to do is to use a visual vocabulary that is composed of simple primitives, 7 primitives in this case, and then recreate these sketches using only these primitives, and then eliminate the primitives that are not necessary for recognizing this object. And then we can use this in communication, like in a game like Pictionary. One of the agents starts drawing the concept, and the second one tries to guess it correctly. If the first one stops drawing new primitives, once the second one is able to guess it correctly. So very briefly how this works. We have sketches, and the parts of these sketches are separate. So we take every part separately, and we also take all our drawing primitives. We determine 7 primitives. We feed that into a stroke encoder that extracts features for us, for all the primitives and for the sketch part. Then we try to match every drawing primitive after transforming them into this part of the sketch. And this we learn fine transformations here. We transform the primitives. The next step is to take these transformed primitives, render them in a coordinate grid, render also the sketch part in the same coordinate grid, where we can compute distances very easily. As another step, we have a compatibility function that measures the compatibility between non-transformed primitives and the sketch parts. Our loss function is composed of these two items, these two parts. One of them takes the distance transforms, the other one takes the compatibility function. We optimize these jointly. Some quantitative results. These are all human sketches. You may be able to recognize them already. Now, with 10% budget, this is the abstraction that our method comes up with. For example, abstracts this shape into a rectangle. With more budget, it adds more and more details. Some of the classes may already be recognizable. And then with more budget, of course, more details get added. which makes the drawing more complex. In some cases, this is not necessary. As a conclusion, learning abstract representations of objects can constrain the system for improved interpretability. So we can use these abstract representations as information bottlenecks for improved interpretability. It's an effective means for evaluating the conceptual understanding of the model. So we can use these abstract representations to see if the model really understands which object they are looking at, and for the whether it does that for the right reasons. And this can help comparing different objects and assess similarity. In the very beginning, I talked about contrastive explanations, and this abstract representations helps with that. Next, I would like to talk about how explanations are tailored for the communication partner. Here, I want to use this simple game that two agents play with each other. The first one picks one of these images. They are presented always the same images. One of them picks the image, describes the image to the second one, and the second one, based on the description, should pick the correct image. Of course, if the second communication partner sees the world in the exact same way as the first one, then this, and if the first one is able to describe the image correctly, then this is a trivial task. But the second one has some form of disability. In this case, it is colorblind. So if the description is about colors, uniformly randomly, this model is going to fail in picking the correct image. And this will get communicated to the first agent. And over time, by playing this game with each other many, many times, the first one realizes that the second one cannot see colors, so it updates its descriptions. Although the most discriminative property still could be the colors, it doesn't mention the colors, but mentions shapes. In this case, this helps the second agent pick the correct image. So we again have a speaker and a listener agent. The listener agent in this example is colorblind. It could be other disabilities. We tried many in the paper. So we extract image features from them, both of them, and these parts is the same for both of the agents. And then we predict attributes in both cases. And here these two agents might be performing differently. And then we contrast these predicted attributes and say, for example, red beak is the property that gives the highest score. In the beginning of the game, this score gets communicated to the second agent. And the second agent, although it also can predict these properties correctly, there is some noise in the process, and it cannot reveal what it has predicted for these properties. And if red beak property is asked, then this leads to a -1 reward that gets communicated to the speaker. The speaker updates its belief about the listener, and that determines the next question. In this example, I show a gameplay that has already progressed. So the cone beak property gets communicated, although it's not the most discriminated property. And that leads to a positive reward that gets communicated to the speaker, and the speaker understands that it started communicating correctly with the communication partner. So if we look at some results, the most discriminated property is brown back. In this example, the chosen property is brown back in this example for these two images. And this leads to the wrong decision for the communication partner. It picks this one, which is incorrect. in more games, the discriminative property is still color-related property, but the chosen one is patterns or shapes-related property that leads to the correct decision. In the game 100, the conversation seems to have converged. Although the most discriminative properties are always related to colors, the chosen property is always patterns or shape-related properties that leads to the correct decision. I would also like to talk about Now probably we can hear us. Sorry, we forgot to unmuted ourselves, but the people still in the chat, and we would like to thank you all for the listening. And we also would like you to thank the audience in the hall. And this was the end of our workshop. And thanks for all for your participation. And yeah, see you in the next workshops.